Okay, so welcome everyone to the second part of this course. So let me introduce myself a little bit. My name is Vasu Pampacharapong, and my nickname is Kun actually. So you can call me Ajahn Kun or whatever you feel preferred. Okay, my office is on the second floor. Okay, well, let's see. I need to pin this, okay? All right, so my office is at room number CB2228, which is in the chemistry 2 building, right there, the older building you saw. And here's my email address. But if you want to ask me any questions or anything, maybe nowadays, this is the old slide, but now that we have Microsoft Teams, so if you have any questions or anything, so you may send me the messages on MS Teams first, and then if we need to meet one-on-one, and then we'll decide whether what we do next. Okay? So, okay, Ajahn Kalapa, you have anything to talk to the students?
เด็กลืมสมุดไว้ค่ะ
อ๋อ
แต่เมื่อวานที่ฝากคืน
โอเคครับ ได้ครับ โอเคครับ Okay. Well, I think Zoom got lost for a little bit, so let's wait for a second. The network is unstable. Okay, so sorry about that. So the internet just went down for a little while, so now we're back here. Okay, so basically, what I want to tell you is just the basic information how you contact me on the previous slide. Okay, so do not hesitate to ask any questions if you have one, okay? I would love to answer them all. So, let's first talk about what we are studying for the second part of this course. There will be 3 main topics, and we will cover chemical equilibrium, thermochemistry, and electrochemistry. So these are the 3 topics that we will cover on this part of the course. And only 2 of these will be on your midterm, which are the chemical equilibrium and thermochemistry, just part of it, okay? So part of thermochemistry will be on the midterm. I will tell you once we get to this topic, which exact part will be on your exam, okay? And the rest will be on your final. So, let's talk about the first topic that we'll be covering for this part, which is chemical equilibrium. So, in this unit, if you have finished it, if you finish, you should be able to write expressions for the equilibrium constants and also calculate the equilibrium concentrations given all the initial concentrations and anything. And then you should be able to recognize the relationship between equilibrium and kinetics. And then you should be able to identify the factors that affect the equilibrium according to Le Chatelier's principle. And then, last thing, you should be able to tell the direction of reactions relative to the equilibrium using the reaction quotients. So these will be the key goal that I expect you to know. Okay? So let's begin. So before we start, when you think of the word equilibrium, what do you think that exactly means? Just tell me, what do you think it means? Equilibrium. What does it mean? Something that balances out, right? Something that is in a state where it doesn't change anymore. So that's a word in Thai we call Somdun. But actually, equilibrium, if you actually look at the word, you can see that equilibrium has this little thing, equal. Of course, that's the same as equal, okay? So, when you actually see this kind of thing, you should think, oh, there must be something kind of equal in this thing. But what exactly are equal? So, let's focus on that, okay? In physics, equilibrium means equal in force, right? So you can see this photo right here. So have you ever played this thing when you were young? Maybe not, but when I was young, I play this all the time with my sister. So basically, what is this called? Do you know the English name? What is this called? A seesaw. That's correct. So if you ever play a seesaw, so basically if you and your friend has equal mass or equal weight for that matter, and if both of you sit on the seesaw, what happens? The seesaw balances itself, right? It doesn't tip anyway, right? So that's the equilibrium in forces on both sides. So that's how equilibrium means in physics. And on the left-hand side, so you have this weighting scale over here, right? How does this work? So basically you put something that you want to weigh, and then this thing reads the weight by knowing that there must be the equilibrium in force at some point of the spring, and then they read the weight. It reads the weight by just calculating from the equilibrium the balance between the forces. Okay? That's equilibrium in physics, but what about in chemistry? What should be equal in chemistry to be called equilibrium? So, it looks like this actually in chemistry. Let me see if I can play this video. It looks like it got stuck. But anyway, maybe you can see this example later on. I might give you some video for you to look. But basically, let me explain to you what this thing is. So, in this video that's supposed to be able to play, you have this reversible reaction going on between nitrogen dioxide in the gas phase, which goes to a dimer, which we call it N2O4. Okay? So, the main thing here is that this NO2 gas has the brown color, right? While N2O4 is colorless. So, what would you expect to happen in this test tube? So we may begin with much more NO2, right? And as the time progresses, you get more N2O4. But if you let this reaction run for a long time, what would happen is that eventually the color in this test tube will remain constant, right? Will remain the same. What does that mean? It means that once you see the color remains unchanged, what happens here is that, you can say that the concentration of both the gases here no longer changes, right? They stay the same. So when you let this thing run, this is too brown, so when you let this thing run as N2O4 form, the color will get lighter, and then eventually it stays the same, right? When the color stays the same, it tells you that, we have reached the equilibrium of this reaction, where the concentrations of both gases are constant. That is the reason why you see constant color. Okay? That's equilibrium in chemistry. Okay, so what you just saw in the video is that you see some changes in concentration over time, but as the time reaches some point, let's say over here, you can see that the concentration of reactants steadily going down until it reaches this point, and then the concentration of reactants remain constant, right? And what about the product? Let's suppose that if you started with just the reactant without any products, then the forward reaction says that the product should start to form, and then you definitely will see the product starts to form like this. But then, once it reaches a certain time, you can see that the concentration of the product also remains constant, just like the concentration of the reactant, right? So this time right here, we usually call it T sub E, which means the time it takes for the reaction to reach equilibrium, okay? This is how we normally call. You may also see another kind of plot, but it tells you the same thing, right? In this case, the product might not form a lot, but you still see the same kind of concept, right? After some certain time, T sub E, you can see that the concentration of both stops remains the same, right? The reactants and the products. And when you see the concentrations of both reactants, the products remain the same, then you can tell that the reaction has reached the equilibrium. Okay? So let me ask you this question. You can see that when your reaction reaches the equilibrium, it may appear to you that the concentrations of both the reactants and the products remains the same, but does that mean the reaction stop? Does that mean the reaction just stop? Because the concentration remains the same. What do you think? Do you think the reaction stops or not? While the concentration remains the same at equilibrium, do you think the reaction stops or not? What do you think? Would the reaction just stop? No, I don't want to turn into the products anymore, and then the product doesn't turn back into reactants anymore. Do you think, is that the case? Actually, no, right? The reaction still takes place, but at equilibrium, the rate of the forward reaction and the rate of the reverse reaction remains the same. So, if I give you this plot where I change the y-axis, oh sorry, actually let me just draw you this. Now, let's see if I have any. So actually let me draw it in this slide so that you can see it better. Okay, so if I have a plot between the rate and the time. So you can see that if I make a plot, so the reactants. So this red one is the reactant. And let me change the color. So let's say black. Okay? And then black is the product. What do you see here? So you can see here that once the time reaches T sub E, which is the time it takes for the reaction to reach equilibrium, you can see that the rate of the forward reaction and the rate of the reverse reaction stays the same, right? That tells you that actually the reactions, both the forward reaction and the reverse reaction, still take place. It's just that the rate is the same at that point, right? So if the rate going forward and the rate of going back is the same, it means that essentially you don't see any changes, because it's just like you run forward and then you run back at the same speed. It's just like that, right? So essentially you try to run forward and back at the same time, so on average you just stay at the same point. So that's the concept. Okay? Okay, let me erase this. This will be on your video anyway, okay? Because I already recorded this lecture. So we'll save this space for this problem, okay? So let's go back to our slide over here. So, as I say, the reaction did not actually stop despite the color of the gases in the vessel did not appear to change, because it is what we call a dynamic process, right? In fact, even if you reach the equilibrium, you still see the N2O4 molecules dissociate into NO2 at the same time as the NO2 molecules combine to form N2O4. But these two processes are just occur at the same rate at equilibrium. Okay? So, for any reversible chemical reactions, an equilibrium is established when the rate of the forward reaction is the same as the rate of the reverse reaction, right? So this is the condition for your equilibrium. the rate of the forward reaction has to equal to the rate of the reverse reaction. Okay? And since chemical reactions still take place at the equilibrium is said to be dynamical. So, do you know what the word dynamic means? Dynamic means always happening all the time, right? Always taking place all the time. So it means that even though your system reaches equilibrium already, the reactions, the changes are still taking place as we speak, okay? It's not that everything stops once your system reaches equilibrium. Everything still changes. It's just that the rate of the forward changes equals to the rate of the reverse changes, okay? This is a very, very important concept in equilibrium and might appear on your exam too. And that's just a hint, okay? Maybe or maybe not. Maybe I'll be tough or maybe I'll be kind. Who knows this year, okay? Let's see. Let's hope that I'm a kind person. Let's hope, but maybe not, okay? All right. So we talked about equilibrium, and then there's another concept that you should know, which is the equilibrium constant, right? So what is the equilibrium constant? So basically, we can say that we can calculate some kind of constant because we know that when your reversible reaction reaches an equilibrium, the concentrations of the reactant and the products will remain the same no matter what, right? And because of that, let's say if you are given this reversible reaction, AA plus BB goes back and forth towards CC and DD, then if this reaction reaches equilibrium, the concentrations of A, B, C, and D remains constant at equilibrium, right? So, when this reversible reaction reaches equilibrium, as the concentrations of A, B, C, and D are all constant, so we can write a constant called K sub C by taking all these concentrations and then divide them together. The format of this constant is that you put all the concentrations of the products on the denominator and then all the concentrations of the reactants in the denominator. Okay? So you can see here that the pattern goes like this. K sub C equals the concentration of C raised to the power of this small c, which is the stoichiometric coefficient of C. Just that, right? And then you have the concentration of D raised to the power of the little d. And of course, this little d is just the stoichiometric coefficient of D. Okay? That's your denominator. Okay? It has the concentrations of all your products, species, raised to the power of their own stoichiometric coefficients. Okay? And then on the denominator, you have the concentration of A raised to the power of this little a right here, which is the stoichiometric coefficient of A. Right? And then you have the concentration of B raised to the stoichiometric coefficient of B. Okay? So this is the main format. This is the definition of what we call K sub C, which is the equilibrium constant, right? This is your equilibrium constant. And this subscript C denotes that it's calculated from concentrations. Okay? So that subscript C denotes that your equilibrium constant is calculated from concentrations. You see case P in this chapter as well. It tells you that that is your equilibrium constant calculated from the pressure. Okay? But for now, let's focus on case C first. Okay? And this definition. Because we use that and to get you familiarized to this concept. Okay? Any questions for now? Okay, let's move on to the next slide. Remember, if you have any questions later on, don't just let it hands on like that. Feel free to send me messages on MS Team. Okay? Please do. Okay, so let's talk about some types of equilibria. Okay, equilibria is the plural of equilibrium, basically. So let's talk about homogeneous equilibria. What does the word homogeneous mean? Geneous actually means the substance, the phase, right? What about homo? Homo means same, that's correct. So homogeneous means of the same phase. What does that actually mean? It means that you are talking about the equilibrium that occurs in the same phase. For example, reactions that is taking place in the liquid or just in the gas. Okay? That is homogeneous for you. So in the case of a solution phase reaction, which is the reaction that takes place entirely in the solution, we typically calculate the equilibrium constant by using the concentration, thus the case of C, right? For example, this reaction. This is the dissociation of CH3COOH. Do you know what the name of this compound? CH3COOH. Do you know what the name of this compound is? It's in your kitchen. You use it to make your foods sour. It's vinegar, actually. And it's the common name of your vinegar is acetic acid. Okay, this thing is acetic acid. You see that in Ajahn Pulapa's part as well when she talks about acid and base reactions. Okay? Or vinegar. It's the same thing. So this thing basically tells you that acetic acid or your vinegar can dissociate in the solution into H plus and CH3COO minus ions, right? And of course, this is a reversible reaction. And this reaction at some point will reach the equilibrium. So if I am to write down the equilibrium constant of this reaction, so from the definition that I gave you from the previous slide, you can see that I need to take all the product species, which are H plus and CH3COO minus, and take their concentration to be on the denominator, just like this, right? Multiply together, and then each of them would raise to its own stoichiometric coefficient. But all of these are just one anyway, right? So that's your denominator for this equilibrium constant right here. What about the denominator? The denominator comes from your reactant, right? Which is only CH3COOH. And then we raise that only to the power of 1. Why? Because the stoichiometric coefficient of that is just 1. So that's the equilibrium constant of this reaction in the solution phase. Okay? And then for the gas phase reaction, which means that they are reactions that only take place as gases. Okay? You can write the equilibrium constants in two ways, right? You can write one as case of C using the concentration of the gas. Another way that you could also write the equilibrium constant in the gas phase is what we call case of P as well. So what's the difference between case of P and case of C? As I told you earlier, case of C means that that's your equilibrium constant that comes from the concentrations, right? But for this, we can say that this subscript P means from pressure. right? So you can calculate this equilibrium constant when your reactions are in the gas phase, right? You can use the partial pressures of each gas to calculate the equilibrium constant K sub P for the case of gas phase reactions as well. Okay? So you either calculate K sub C or K sub P for gas phase reactions. Okay? Any questions? Alright? So, let's move on. So let's actually do some problems here. So I want you to write the expressions for the equilibrium constants for these reactions. So let's say first for A. So how do I write the equilibrium constant for A? How many ways can I write the equilibrium constants for A? One or two? Two, right? I can write these in terms of K sub C or K sub P, right? So let's talk about K sub C first. So what's the expression for K sub C of this reaction? Can anyone tell me? What is the expression for K sub C in this reaction? The concentration of what? CO, right? Carbon monoxide raised to what power? 2, right? And then what? The concentration of what? Times the concentration of O2 raised to the power of what? Just 1, right? Is that it for my denominator? Yep, that's it. And now the denominator. So what's on the denominator? The concentration of CO2, right? Raised to what power? 2. That's correct. So that's your K sub C. Now, let's talk about K sub P. It's the same kind of thing, right? So K sub P of this reaction means that I have to write it this way. So it's going to be the partial pressure of CO raised to the power of 2 times the partial pressure of O2 divided by the partial pressure of CO2 raised to the power of 2 as well. So you can see that the definition on how to write the expressions for K sub C and K sub P are the same thing, except that for K sub P, you use the pressure, but for K sub C, you use the concentration. Just that. It's easy. Okay? Now, let's talk about B. So, of course, I can also write both K sub C and K sub P because this is a gas phase reaction, right? So what's K sub C for B? What is K sub C for B? The concentration of what? O3, right? What's O3 anyway? Do you know it? Ozone. Okay? Raised to the power of 2, and then what? Divided by the concentration of O2 raised to the power of 3, right? And for K sub P, it's the same thing. So it's going to be the partial pressure of ozone raised to the power of 2 over the partial pressure of oxygen raised to the power of 3, right? I'll change the color for the next one so it's clear to see, okay? So for C, you see this reaction to H2 plus O2 goes to H2O, 2H2O. Okay, this is the formation of water when you burn hydrogen with oxygen. Okay, so how do I write the equilibrium constant for this problem? K sub C. So it's going to be what? It's going to be the concentration of water raised to the power of 2 over the concentration of H2 raised to the power of 2, and then the concentration of O2. That's just it, right? And then for K sub P, it's the same thing. It's the pressure, partial pressure of water, vapor, raised to the power of 2 over the partial pressure of hydrogen gas raised to the power of 2, and then the partial pressure of O2. Just that. Okay? What about D? It's still similar, right? Now, tell me, how do I write the K sub C for D? the concentration of what? NH3 raised to the power of 2. That's correct. And then for the denominator, what do I have to write? It's going to be the concentration of H2 raised to the power of 3 and then times the concentration of N2. Okay? For case B, it's the same thing. So it's going to be the pressure of ammonia raised to the power of 2 over the pressure of hydrogen raised to the power of 3 times the pressure of nitrogen. That's it, right? Let me zoom this in so you can see that. Okay? And for the last part, so how do I write my equilibrium constant? Can I write that as the case of P? No, because this reaction is actually in the solution phase, right? Not the gas phase. How do I know it? You can see that AQ right here, right? What's AQ? AQ means aqueous, right? It denotes that your reactants or your products are in the aqueous inside the solution of water, okay? So it means that I can only write case of C for this one. So what's case of C for this reaction? It's going to be the concentration of H plus raised to the power of just 1, right? Times the concentration of SO4 2 minus, right? Over what? The concentration of HSO4 minus. Okay? That's just it. So, see? It's easy. So now you know how to write your equilibrium constants, right? That's easy. But it's not the only easy part. There will be harder parts for sure. So now we'll get to that real soon. Now, let's talk about the relationship between case C and case P for gas phase reactions. Okay? So, if you go back a little bit to your high school, so you know that we have this beautiful equation that we call PV equals nRT, right? Any one of you haven't seen this equation? So I suspect you all have seen this equation, right? You all have seen this PV equals nRT equation from high school, right? You should, because if you didn't, then how would you graduate? Okay, you should. So we have this relationship PV equals nRT for the ideal gases. So if we rearrange this equation a little bit, so we have here P equals N over V times RT, right? And this is something, N over V. What's N? N is the number of moles of the gas, right? The unit of this is, of course, mole. Okay? What about V? V is the volume of the gas, right? Which has the unit of liters, right? So take a look at this expression. We have N over V. So if you divide N over V, when you have N in the unit of mole and V in the unit of liter, what you get is something we call the concentration, or C, which is in the unit of moles per liter. Okay? So anyway, all those concentrations that you use in the case of C, expression needs to be in the unit of moles per liter. Or there's an expression for this unit which we call it the molarity, or molar. Okay? Moles per liter, we also call that molarity. It's the same unit. Or we short for that as M, the big M. Okay? So we have P equals the concentration of the gas in molarity times RT. Okay? So, what does that tell you? So if you have this reaction, AA plus DP goes to CC plus DD. Now, if I write case of P of this reaction, this is what I will get, right? So I get the pressure of C raised to the power of C, and then I have the pressure of D raised to the power of D over the pressure of A raised to the power of A, and then the pressure of B raised to the power of B, right? Then I use P equals CRT from above, and then substitute that expression into P, right? So the pressure of C is nothing but the concentration of C times RT, right? So it comes from this. So I just substitute this into this to get this, okay? Now, the pressure of C is just the concentration of C times RT, right? The pressure of D is just the concentration of D times RT, so on and so forth. The pressure of A is just the concentration of A times RT, and the pressure of B is just the concentration of B times RT. That's it. All these raised to the same power, okay? So, if you work on this expression a little bit, this is what you should get. You should get something that looks like this, right? The concentration of C raised to the power of C times the concentration of D, blah, 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 blah. What is this thing anyway? This thing is the case of C, right? But it's not just that simple. Case of P does not exactly equal to case of C, but it equals to case of C times this expression right here, which is RT raised to the power of C plus D minus A minus B. Okay? How do I get that? Well, it's because that's from your high school math, right? When you multiply two exponents with the same base, then you have to add the exponents. Okay? That's your high school math for you. So I simplified this thing further as case of P equals to case of C times 0.0821, this thing is just your R, right, times the temperature, all these, raised to the power of delta N. So what's delta N anyway? I just write this to make it short, but let's call this delta N as the difference between the stoichiometric coefficients of the products as opposed to the reactants, right? So I take the ones from the products first and then subtract, add them together, and then subtract with every stoichiometric coefficients from the reactants, add to each other, right? So that's why I add C and B first, and then become C plus D here, and then I add A and B, so I can put the parentheses on this and convert A minus B to A plus B. Right? So in a sense, this exponent is C plus D minus A plus B, which is the same as C plus D minus A minus B. That's just a little math, right? These two things are the same. So I just put these two in parentheses to illustrate that this is the sum of the stoichiometric coefficients from the products. And this part is the sum of the stoichiometric coefficient from the reactants, right? So that's delta N, what delta N means. So basically you add all the stoichiometric coefficients from the products first, and then you add the stoichiometric coefficients from the reactants, and then you subtract the one from the product with the one from the reactants. That's just your delta N, okay? So what if delta N equals 0? If delta N equals to 0, it means that your case of P of the gas will be the same as case of C. Okay? Because this thing raised to the power of 0 will just get you 1. Okay? And the most important thing here is that this temperature that you use in calculation needs to be in Kelvin only. Okay? You can't use degrees Celsius in that. That's going to be wrong, for sure. Use Kelvin only. Okay? Any questions? Going once? Going twice? Okay, good. Let's move on to this question here. Methanol can be produced from this following reaction below if Kc of this reaction is 10.5 at 20 to 20 degrees Celsius. I want you to calculate the Kc for this reaction at the same temperature. So, what we need to do, is this a gas phase reaction? Is this a gas phase reaction? Yes, it is, because everything is in the gas, right? In the gas phase. So, how do I calculate K sub P? Well, this is what you know from the previous slide, right? K sub P is K sub C times RT raised to the power of delta N. Right? What's delta N here? 0? Really? No, I don't think so. What's delta N? Delta N is the sum of the number of stoichiometric coefficients from the product. So just one from methanol, right? That's it. And now minus the sum of the stoichiometric coefficients from the reactant side, which is what? 1 from CO plus 2 from hydrogen, right? And that gives you what? Minus 2. Okay? So, that's your delta N. So now let's plug everything in. K sub C is 10.5. Now, times R, which is 0.0821, times the temperature. So what should I plug in for the temperature? 220? No. What should I put in? What do I have to add to 220 to make it Kelvin? 273, right? And that gives me 493.15 Kelvin. And everything in this parenthesis raised to the power of what? Minus 2, right? So, can any one of you use the calculator and tell me what the answer is? I won't do that for you. I want you to do it for me. What's the answer? Take your time. Zero point one? Zero, how many zeros? Behind the decimal? 2, right? So it's 0.001. 64. I don't know if this answer is correct, so you maybe go and check this number here, alright? But it looks correct to me, so that should be it. Okay? We don't typically put the units on for the equilibrium constants unless we use that in calculation where you need to combine all those units in the conversion factor, okay? But normally we don't use the units here, okay? So, any questions on this example? All right, let's move on. So, I'll give you 5 minutes for this example to think about it, and then I'll give you the answer. Okay? Or anyway, I want you to calculate both case C and case D. Okay? So if you have the answer, just let me know, okay? But if not, maybe in 3 minutes, I'll give you the answer. Alright, anyone got the answers yet? No? It's okay. Let's work on this together, okay? So, let's first compute case C. That's easy. So, what's the expression for case C? That's the concentration of NO2 raised to the power of 2 divided by the concentration of NO also raised to the power of 2, and then the concentration of O2, right? So let's plot all those numbers in. So it's 15.5 raised to the power of 2, right? The belief is correct, so the concentration should be in molar, okay? Divided by this concentration of NO, which is 0.0542 raised to the power of 2, and then the concentration of O2, which is 0.127. That's it. So maybe you already got this number. What's the Kc for this reaction? What's Kc? 6 what? Well, let me Google it. Actually, I mean, use Google to compute this thing, okay? It's fast. 15.5 raised to the power of 2 divided by what? Okay, maybe you get the same. So it's 6.44 times 10 to the power of 5. Right? Is that the same as what you got? Right? It should be. Now, let's calculate K/P. How do you calculate K/P? Well, let me use a different color here. So we know that K/P is just what? K/C times RT raised to the power of delta n. Right? But now I want to compute K/P from K/C. So we've got K/C, and now we have to figure out delta n. What's delta n? Delta n is minus 1, right? So it's going to be this 6.44 times 10 to the 5th times 0.0821 times the temperature to 30 degrees Celsius. So what is it? It's 503, right? 0.15 raised to the power of minus 1. So what's your answer? I mean, if you use 503, it's fine too. 3.76 times what? 10 to the power of minus 8. Really? I don't think so. Let's check. Okay, in fact, this is not correct. It's actually 1.56 times 10 to the 4th. Maybe you can check later on at home whether I did this correctly, but I put this number on Google. It shouldn't be it should be correct anyway, but maybe I typed it wrong. Maybe you check, but I think this is right. Okay? It's just this number divided by 0.0821 times 503. It's just that. That's simple. Because when you raise this to the power of 1, it's just this. Okay? So it should be something less than 10 to the power of 5. Okay? So, any questions? Alright? So that's an example for you. We talked about the homogeneous equilibrium. Now, we'll talk about heterogeneous equilibrium. So how's that different from what we learned earlier? Homo means the same, right? But what about hetero? Hetero means different, right? So now we are talking about equilibrium that comes from reactions that take place in the different phases. Okay? What does it mean? What do I mean by that? So let's see. Sometimes you have this reaction that take place in more than one phase. For example, maybe you have something in solid and aqueous phase at the same time. Or you may also have your reaction in the solid and the gas phase at the same time as well, right? So the only thing that we need to consider is that when you have such reactions, pure solids and liquids are not actually considered or included in your equilibrium constant. Why? Because when you have pure liquid or solid, it means that they are considered to have normally constant concentration, right? So that's already a constant. So when you put in another constant that doesn't change anything, you don't really change the meaning of your equilibrium constant, right? So when you have pure liquid or pure solids appears in your reversible reaction, you don't use them in your equilibrium constant expression, right? So look out for those. So let's take a look at our example here. I want you to write the equilibrium constant for these two following reactions. So let's take a look at the first one, AgBr, solid phase, goes to Ag plus in the aqueous phase and Br minus in the aqueous phase. So what is going to be my equilibrium constant here. So it's going to be what? The concentration of silver plus times the concentration of, Br minus. Do I put anything on the denominator? Do I have to put HGBr in the denominator? Well, I could try. And let's do that. But what's HGBr? Which phase is it in? It's in solid phase, right? So this thing is in the solid phase. So it starts to have constant concentration, right? So this is essentially a constant, right? And here we are saying that this case of C needs to be a constant. A constant times a constant or divided by a constant also remains a constant, right? So we don't actually consider this because it's a solid that has a constant concentration. So the equilibrium constant expression of this reaction is just this. The concentration of silver plus times the concentration of Br minus. Okay? So we don't consider the silver bromide at all because it's a solid with constant concentration. Okay? So that's for HGBr. What about the second reaction? Well, it's like everything homogeneous, but there's a gas phase. So let me calculate K sub P for this because the pressure is more convenient than concentration for gases. Well, what's my K sub P for this reaction? What's my K sub P for this reaction? Well, I can try to write the pressure of PCl3 raised to the power of 4 over the pressure of Cl2 raised to the power of 6 times the pressure of P4 raised to the power of 1. But wait a minute. PCl3 is a what? It's a liquid, right? But P4 is a solid. These two are thought to have constant concentration and does not have any defined pressure in the gas phase as well. So why the hell should I consider those two? So it's just that. Just this. Okay? So now you get the idea. When you have equilibrium that is in the heterogeneous phases, you only consider the gas phase, the part with the gas phase, or the part with the liquid phase, to put those into your expression for the equilibrium constant. You don't consider the pure liquids and pure solids at all, because they are thought to have constant concentration, and that will change the fact that your equilibrium constant is a constant. So that's why we don't consider it. Okay? Any questions? All right, let's move on. So that was the heterogeneous equilibrium for you. Now let's talk about multiple equilibrium. So what about when you have two reversible reactions that are in the equilibrium? What happens when you add two chemical equations together, and how would that affect your equilibrium constant? So let's take a look here. If there exists more than one reaction in equilibrium, so the K, or the equilibrium constant of the sum of all the reactions, is the product of the equilibrium constants from each individual reactions. Okay? So let's take a look here. For the first reaction, we have A plus B goes to C plus D, right? So the first equilibrium constant is just the C times D over A times B, right? That's easy. For the second reaction, C plus D goes to E plus F. The equilibrium constant of the second reaction is E times F over C times D. That's obvious, right? Now, if I add these two reactions together. So what's going to be my resulting equation? C plus D will cancel each other's out, right? So I will have this sum reaction to be A plus B plus goes to E plus F, right? And if you try to write the equilibrium expression, for this it's just E times F over A times B. But wait a minute. Now, what's K1 times K2? Okay, so if you take this and then times this, the C plus D part cancels out, right? And you got what? E times F over A times B, right? So you can see that if we add two chemical equations together, that's how the equilibrium constant is affected. So the new equilibrium constant of the sum reaction is just the product of each individual equilibrium constant from the sub-reactions. Okay? So you can see that. Any questions? Alright, what's the time now? Oh, I think we are pretty good in time. Do you guys have any questions for today? Alright, so everyone, you have my contact information. So from now on this part, if you have any questions, send me messages through Microsoft Teams and I will answer, right? So the slides will be for each individual lecture day, right? And today, I think that's it for now. So next Monday, we'll also meet here in this room and also through Zoom. And the video of this lecture will be available shortly, maybe today, maybe tomorrow on the YouTube playlist that I posted. So maybe look out for all those videos, okay? So all the videos during my part of the lecture will be posted on there, okay? Any more questions? I think that's it for today. So I'll see you guys again on Monday. Have a good weekend.
Thank you.